Can you all see if I write like this? Yeah, just as a check. Okay, very good. Are the Zoom people online, Yuli?
Yes, I expect so.
Okay, I can start.
Yes, please.
I can officially start. Thank you very much. So, welcome everyone. We're, I forget which number. I think it's the problem solving session 5.
Oh, who counts?
Huh?
Who counts?
Who counts? Okay. So problem solving session today with quite a nice cozy setup. So we're going to talk about one of the problems that are on the presentation. It's problem number 11. And if we have enough time, which I doubt, but let's see, maybe also a little bit about problem number 13. But starting with 11, which is about the overview of the Gen equations. So what I'll do is I'll try to go through the problem slowly. You'll also get to work every now and then, helping me, doing calculations and so on. And so we work through it. The goal is not to finish the exercise. The goal is just to learn until time is up, more or less. So what is this problem about? Well, it's a long one. I don't know if you looked at it, but you can find it on the list. It's a long one. And you can divide it in several steps. So let's first discuss the steps. What are we going to do? Well, we're going to derive and eventually also solve these equations. And this is the plan. First, we will introduce an effective Hamiltonian that describes the ground state of a superconducting, because this is all about superconductivity, superconducting metal. That's the first part. Then, next, a transformation comes. We will use transformation to quasi-particle form of this Hamiltonian. Then, step number 3 of 4 in total. This transformation, what is it about? It's defined by the BdG equations.
I'm sorry, Miriam, there are requests for you to write in larger letters.
Oh, okay. Okay. Like this, I can also do like this. It's better like this. For the people.
Yeah, there are conflicting interests, but if you kind of write it large, I guess everybody will be satisfied.
Ah, okay. Now the common is okay. I will write larger. By the sound is good, Yuri, for the people at home. They can hear.
Yeah, at least me.
Okay. So this transformation we're going to apply is defined by the BdG equations. And then step number 4 does not fit. So next board, because of big writing, I have to go to next board. Solutions. Finally, we will look at solutions, by which I mean the energies of the quasi-particles and they determine the energy of the ground states. Yeah, so we'll look at the energy of the quasi-particles and the energy of the ground states, which also energy ground state. Yeah, GS is always ground state. BdG is always what we do. Okay, so this is the plan. This is what we're going to do. Part A. First question, first task for us is to calculate the total energy over supernovae. Right? Now how? There has to be some starting point. Starting point is the following expression for the energy. It's given in the exercise. E, is it better now? Can they see?
Yeah, sure.
Okay. E is, and we define it as minimization problem, which you have seen before, I think. Minimizing over delta. And then there is expectation value of Hamiltonian HS. I will define HS in it, plus another term, volume divided by U delta squared. Let's label this one. So this is the energy we're going to find by a minimization procedure. What is this, people? Is U. Does anyone remember what it is? The what? Potential energy. Yes, can you be more specific? So it's a type of interaction that leads to potential energy. What type of interaction? Who remembers? Contact interaction. Yes. Yes. This U is, so it's U absolute value, so it's the strength of the contact interaction. And this contact interaction, U of R, only acts locally. You remember, it's a delta function expression. So only if I'm at that location, I feel the U. What's the sign of U, people? Is it repulsive or attractive? Attractive. So U, strength, negative. U, smaller than 0, it's important. We also have absolute value entering. Attractive. Anything else we need to define? This is supposed to be capital U, the volume. You can also write V or as you like. Now this Hamiltonian HS, we still have to define. HS is given by H1, kinetic part, H1 kinetic part of the Hamiltonian. And then there is the interaction part, sum over K, delta, and then here are the operators. Same notation as in the book, of course, so familiar, I hope. C minus K spin down, plus permission conjugate term, delta star, C minus K down, and C K up. I'm going to stop talking for a little while, because now you have all the ingredients to do this minimization. Have a try together with the neighbors. So, your neighbors. So to do, and then we look at what we could get a little bit later. To do, evaluate this energy, equation 1, it is. Did I forget a dagger? Yeah, I forgot one here. Sorry, not. Yeah, so it's 2 creation operators to an erasure. Thank you. Please speak up anytime I forget signs, daggers. It happens. So evaluate 1 by minimization. Find this energy and do the minimization with respect to delta star, because then you find an expression for the optimal delta. You can also minimize with respect to delta itself, but it doesn't really matter. But if you do the deltas. So have a try. And then what you should find, you find the delta that minimizes the energy. And that is an expression that I'm going to use. See if you can. It will take something like maybe 5 minutes or so. Yeah.
Is it phi of state?
Sorry, is that?
The state of state.
Yeah, the wave function here, you mean? Yes. Yeah, okay. But you minimize.
No, yeah, I know, but
okay, yeah, fine. Yes. I already have a coverage. Sorry, confusing. He sent me that was, and I think you did it as well. It's you divided it like it's a different one. So the question A was a different one from the B, and so for you this is easy. Yeah, it was a bit of a mix up. For most of the people. Yeah, that's a good example. Yeah. I wrote a news also, and I put it out, and also this, and also about the presentation, he can't present because he has. Yes. I don't know. Excellent. But I think it's nicer if the family presents, we like you they present. Part of the exercise is to stand in real life. Yeah. Last year it wasn't like that, but every right? So it's if it's no trouble, then I'll see, because we're in Pulse, which is a different building. I don't know what the facilities are. So
I mean, it's easy.
So you take this complete thing, and you delta star is only numbers, right? It's in this HS here. So leave all the operators, leave them in your expression. Don't evaluate. Okay.
I'm just trying to figure out what's the derivative of the number with respect to its complex conjugate? Is there any relation, or is that just zero?
Oh, but you know.
Really, I have forgotten.
Then treat them as independent variables. So you minimize with respect to delta star. So only the terms that have delta star in them.
And delta, then of delta to delta star.
Yeah.
All right.
Have a try. See what you get.
Ik ben maar een beetje aan het nadenken.
Ja.
Maar deze valt weg, dit valt weg, deze wordt waarschijnlijk 0.
No, but okay. I'm going to say something. So thanks for bringing it up. So don't evaluate anything. Huh? Don't try to evaluate this expectation value, for example. Only minimize. So differentiate this expression with respect to delta star. That's all you have to do. Don't try to evaluate. Keep them all in there. It's easier, I think, than you may think it is. Maybe. I'm going to write the result. It's also in this equation, so you find it in the book. So optimal delta should be negative U over volume, and then you have the sum over K. You see, don't evaluate these sums and so on. Just keep them in your answer. Sum over K, psi, and then there is this Z operator. Also familiar. Let me just write it. The Z operator, the definition, the pairing operator. Well, that's not an official name, but okay. It's the product of C, K, minus K, spin down, and C, K, spin up. So it annihilates 2 electrons, one with momentum K and spin up, and one with momentum minus K and spin up. Because those two are the ones that pair up. Okay? like, now that we have found optimal delta, we can substitute it in here and find the energy explicitly, yeah? So the minimized energy. So substitute, let's do that last step. Substitute 3, that's delta, back into 1, that's the energy. And you find that E is equal to psi, kinetic energy. Expectation value of the kinetic energy? Yes, please.
I don't quite understand why we did the minimization with respect to delta star.
You can also do it with respect to delta.
Okay, so
Then you find an expression for the optimal delta star. Right? And they're each other's complex conjugates. So it's equivalent. I was just a little lazy in the sense that this gives me immediately delta if I pick delta star. No deep reason. And then second term minus mu over u. And then we have absolute value delta squared. And this is approximately, which is very nice, kinetic energy, yeah, expectation value of the kinetic energy. And this is the expectation value of the potential energy, approximately. So I can also write this as H1 plus H2 and the whole thing, matrix element. Kinetic part, potential part. Because this H2 from the derivation in the book is approximately this. Part B, we have to go until G, so it's a long exercise. Now, let's generalize this Hamiltonian. This Hamiltonian HS, we're going to generalize to an inhomogeneous unit. HS equation 2 inhomogeneous. Superconductor. So we make it a little bit more complex. So HS now becomes sum over n and n of C and dagger C. I'm never going to fit it. Okay, let's see. 1/2 delta nm. Now, space. Okay. Plus, I continue here. Yeah, so the Hamiltonian, it's split between two boards, but it has 3 terms. Yeah, here, one half the interaction term, and then the second half the Hermitian conjugate of it. Okay, now there is a claim. We claim that this delta NM must be antisymmetric. So delta NM is minus delta MN. Yeah, if I switch the indices, must be a minus sign in front. Why? Can you think of a reason why that must be the case? And you don't need to do calculations for it. Yes?
Hamiltonian remission, so we do the remission of alpha, you should find the delta, you should find that symmetric.
Do people agree? Is that true? I agree with you that the Hamiltonian is not true. But does that give me this relation? What do others think?
Commutation relation, you change N and M because they have like subincluses. You get a minus sign and should cancel with the minus.
Yes, yes. I think the more direct way is using commutation, or rather anti-commutation relations for the C's. So they anti-commute the operators. So anti-commutation gives you a minus sign. That minus sign must be cancelled. So only the antisymmetric part of delta survives. Symmetric part must be 0. So, good. Delta is antisymmetric. Now we would like something. We would like to pair operators. But these are still single particle operators as usual. So we would like, and the reason is a little bit, this is nice and familiar. Product of a creation and an annihilation operator. Here you don't have that. You have product of 2 creation and 2 annihilation operators. Let's see, because it will be convenient later, whether we can bring this into a form where you also have, again, have a product like this. So, we would like to pair creation and annihilation operators. And one way to achieve it will turn out to be that we double the amount of operators. We double the set of operators. So, making things more complicated, maybe, you think. Doubling doesn't sound like simplifying, but it will have advantages. And to do this, we introduce a new set of operators. They are called D. D with subindex N and alpha. It's an operator. And by definition, it is equal to the annihilation operator Cn for alpha being an electron, E stands for electron, and it is equal to the creation operator Cn dagger for the holes. Maybe not something that you would think of, and that we would think of ourselves immediately, but given this set of operators, it will turn out to be very convenient. So these are the operators. Now, let's use them. Using these new operators, show that we can rewrite equation 5. Where is it? Up there, the Hamiltonian of the inhomogeneous superconductor. ask something else. Let me write it here. Now it's a very long sum, the sum over alpha beta, which is electron hole space, electron hole index, and then the sum over n and m, that was already there in equation 5. And now I have dn alpha dagger, Hamiltonian n alpha m beta, and then dot continues here. Plus a constant, let's call it E0. So this is the claim. Claim is that by using this transformation, these doubling operators, if you like, you can rewrite this Hamiltonian, equation 5, into that form. Now I must define this part here. So I'm going to write it in matrix form in alpha beta space. So this will be H delta, using the notation from the book, because otherwise it's confusing, minus H, like this. So this Hamiltonian is written in as a 2x2 matrix in alpha beta space. And there's also, remember that these H and delta still have N and M indices. That's important. Yeah, so they've lost their index alpha beta because that is our matrix, but they still have N. This is only to indicate this is only to indicate that I have left out these indices. They're not written explicitly. Yeah. So our next task is to find an expression for E0, for this constant in equation 7. While I wipe the board, the parts that we don't need anymore, have a go at it. See if you can transform equation 5 into equation 7 using these new operators, and then an expression for E0 should follow. Erase much. Only. Yeah, or the other way. Verify that. So you see, in many of these problems, using computation relations is very good. Also in the homework, already combined, say, second, and so on. But also in these types of exercises, rewriting things, nearly always. So work backwards. Let's start with the 7, and then see if you can bring it back to the original.
Ja, dus wat hier mee. Ja,
Risking to state the obvious, we don't have common break. These arrange individual breaks.
Yeah. Sure. Yeah. There's going to be no break. We have minutes to work. Now it's, for example, if you take this, get coffee, go ahead.
Opnieuw ben je gewoon goed uitleggen.
You're just inside it's not your transport.
So, does anyone have an expression for easy one? No, almost. Who's getting close? Yeah, okay. Shall we work a little bit more for someone to reach it? Or do you prefer to finish it all? If you're getting close, let's wait. I am counting on you. Okay. Ja, heel goed. Dat is precies wat ik doe. Is deze matrix dit is maar dus dan krijg je als je deze gebruikt, dan krijg je die wordt weer op, dat is dat die houdt gewoon zijn index en dan wordt het niks mee, maar dan krijg je dus 1 keer. Dat is weer element. En ze hebben beide een index en, want daar doe je niks mee. Maar dat doen ze aan. Ja, zo wat. Daar heb je dan de annihilatie over. Dat wordt ermee bedoeld. Ja, dit is echt een boek.
Ja, nu moet ik weer invullen voor die assessment.
Precies, en dat moet je hebben. Want je oorspronkelijk Hamiltonian gaat alleen maar over N en M. Zo. This term. This one. No, this is just the element of the matrix. So it's a scalar. It's a H and J. So this product. There will be a sum.
No, I think that they should only move the shot by 1 balance.
And it's equal to n, something will happen. And that's something because the delta terms actually, yeah, they're already it's just the first one.
Okay. Volgens mij ben ik gewoon ook normaal. Dat is goed. Hij zit in die mooi. Deze term hier wel. In de term hier wel. Ja, dus D en 1 keer die term. En D en H natuurlijk. Maar dan moet je dus niet dat. Maar alle termen zijn precies.
See, because that's not taken care of, and what you use it and don't do that, you just write out the sum. So both elements in this alphabet side have
The six creation. The six aggregate.
Ja, maar kijk, je moet even kijken, want je hebt die D, zeg maar, en je hebt bijvoorbeeld D en E.
Nee, gewoon CN is annihilation.
Ja.
Van maar CN dagger van een rol. Nee, sorry.
Ja, CN dagger is annihilation van de rol, maar creation van de
same for delta. So instead of having these wheels here, you can write H and N.
Ik dacht al. Nee, want als je een enkele hebt, dan lijkt me logisch.
Nee.
Yeah, and they will minus sign.
Voor die D en
Ja, dat is ook een elektron.
The transport is missing. Someone was very smart.
Remind
Remind me. No, I have to log in.
hij creëert.
So now you have,
Als je een elektron
and once you
hebt,
have these expressed indices, and it already starts to look very much like expression.
Het is gewoon een volle state. En als DN erop opereert, dan
Yeah, it's in the
ja.
this notation is supposed to this is a vector.
You split the sum.
It's a notation. It's not something. No, it's not
And then you say,
something.
okay, you need
This is
one,
the way
I
we
can
define
play
sometimes. It can be ambiguous. Alright.
and then you jump them.
Anyone has E0?
die zijn allemaal hetzelfde.
Dares to make, you have, dare to make a guess, yeah? No. Always. This is something. Because you have a double sum here. Yeah, very good. I'll write it. Since everyone is close and we have to make progress, maybe we can talk about the next part as well. So this, if all goes well, should be this. 1/2, and you can do it, sum over n. And it comes from this term, this whole term, which you have to manipulate. I'm not going to do it, it will take far too long. But it's not complicated, you just have to do careful bookkeeping. Use the anti-commutation relation to rewrite this term number 4. If you write out this entire thing, you will get a sum of 4 terms. The last one usually is this one. And that you have to rewrite a bit using anti-commutation relations. And then there is an extra term appearing. which is this one. So E0 there in 7 is equal to check at home. It's a good exercise. If you didn't reach it completely here, have a check at home. Okay, next one. Okay. Now another rewriting exercise. Because we have to get to the form of the BdG equation, and it goes in steps, like we said. Now, write again the Hamiltonian, HS. It is gone, but it was equation 7. In the form one half, and now again new operators, gamma, this time it's gamma, dagger, EK is the eigenenergy, gamma K, plus E0, so with these energies, EK, are the eigen values of the Hamiltonian equation 8. And this Hamiltonian equation, it was the matrix, the 2 by 2 matrix. And this is big disadvantage of working on Blackboard because you have to wipe it at some point if you get run out of space. And so, but you have it in your notes, I hope. And I cannot record it now. But anyway, you remember, 2 by 2 matrix. Now next task, our next task is to express the new operators, the gammas, in terms of the d's. Express gamma k operator in terms of the d operators. Okay, let me talk a little bit about how to do this. Steps. Things usually go in steps. Now, any Hermitian matrix, you can always write as a sum over its eigenvalues and eigenvectors. So let's do that with this one here, this Hamiltonian equation 8. Right? Step number 1, write the Hamiltonian H, equation 8. It's Hermitian like any Hamiltonian, so you can write it as, or in terms of its eigenvalues and eigenfunctions. This is the standard procedure, right? This is nothing mysterious. So I can write it like H and alpha. I'm going to add the indices explicitly so you can see there's still n and m, and there's alpha and beta for the electron hole space. This will be sum over k, psi, k, and alpha, energy, and then complex conjugate wave function, psi, k, star, and beta. Equation 10. This is. Yeah, so this is my starting point. I start with this Hamiltonian 2 by 2 matrix, and I express it, as you can do with any Hermitian operator, in terms of eigenvalues and eigenfunctions. Now, we use this new expression, equation 10, substitute, step 2, substitute this expression into equation 7. It's also wrong. Okay. Equation 7 minus E0. And then evaluate, as usual. So it's again a bookkeeping exercise, and like the previous one that you all worked on. So let's see what we get. Result, I hope I make no mistakes in all the symbols. Result should be that HS minus E0, so this is HS, is equal to, again, a big sum, alpha, beta, and NM. I have to sum over all of this, and I have to sum over K, because the K is coming from here. I'm substituting this expression. So I have a 5 sums, product of 5 sums. Okay? And then it's a matter of adding everything, D and dagger, sorry, K and alpha. Yes, I hope it's okay. Okay. So, A star, M, beta, D, M. I hope there are no mistakes. Oh, it's okay. I have this one. Yes, I have this one. Yes. Okay, I hope it's okay. If you see daggers missing or so, then please send this to me, because I don't always see them. Next step, 1/2 sum over K. Yes, I'm going to introduce, no, I'm going to compare this expression that I have now written out to the one I'm trying to get. This one, oops, this one here. Yeah? And if you look carefully, we are already there. Can you see it? Because look at where the alpha dependence is, for example. So the alpha and n dependence is only here. And the beta and m dependence is only there. So this sum here over alpha and over n only relates to this term, and the same for the beta and the n. So we have found an expression for the gamma operators. So I'm going to skip this step. You have all seen it. We skip it, we just write down the result. So gamma k is a double sum, n and alpha, or n and beta, if you like, doesn't matter. Psi k star n alpha d n alpha. Task completed. These are the gamma operators expressed as a sum over each of them is a sum over the whole. Part D. Part D is rather technical. I will give it to you as an exercise to solve yourself. It's again, careful manipulation of operators you need and commutation relations. Let's write it, but let's not solve it here because it's a technical and a nice exercise for home. So in part D, we return to one of our Hamiltonians. This is again the one in the matrix form, equation 8 it was. And now you have to prove, that is the task, that if you have an eigenfunction of this Hamiltonian, if you have one, let's call it psi and alpha psi. Oh no, no combination of electron and hole. Electronic wave function, electron-like wave function, hole-like wave function, both index n. Imagine that this is an eigenfunction, you know it to be an eigenfunction of with eigenvalue pk, let's say, and then you prove that the following psi and star, but now whole, psi and star electron is then an eigenfunction of the same Hamiltonian, of course, but with eigenvalue minus. And also find the appropriate anti-commutation relations for the gamma operators. Yeah, so you, from the formulation, you can already imagine that this is writing out exercise, writing it out, keeping track of the indices, using the commutation decision. So the proposal is to leave this for now. I don't know what I did at home. Let's go to the next one. We can still work on together. Solution. I'm going to refer to the book.
If you could still use larger letters.
What, sorry?
Larger letters.
Larger letters, yeah.
But
It's getting
anyway,
smaller
it's
again.
okay.
Yes. Sorry. It's getting too small. Okay, bigger letters. E. E, yes.
Do you use different notation for the eigenfunction improvements? Because you call them psi k, vector k, with
Yeah,
argument
here.
A.
Yeah,
But
over there.
it's the same thing.
It's the same thing. The indices are now written out explicitly, yeah, for the alpha. I mean, yeah, for the electron and all. Yeah. You also had a question? No. Oh, sorry. Okay, I thought I saw. Now we have imagine that we have solved this. We have properly worked through it, and we are convinced of these anti-commutation relations and so on. We now have positive and negative eigenvalues. Let's try to get rid of the negative ones. That's what the next part is about. Getting rid of negative eigenvalues. Yeah. Energies. Let me write energies. That's the goal. Now this again goes through a proving exercise. So we're going to prove that the Hamiltonian PSS, which is equation, let me just check. S. I'm not sure I numbered it. Okay. Let's see. I think it was 11. Mm-hmm. 11 is still out here. No, that's not a Hamiltonian. Okay, so
Then is HN alpha and
let's call this 10 and a half. Yeah? So 10 and a half to solve this problem. 10 and a half can be written as, and now we're only going to have positive energies. So I'm going to watch this. EK is now strictly larger than 0. That's what we're going to work towards. And I have the gamma K dagger, E K gamma K operators, plus another constant. It's not E0, it's a different one. Let's call it EG. Equation 12. And guess what? We have to find an expression for EG. So start with hint. Start with the familiar Hamiltonian. It's now called 10 and a half. HS. And use, but now we are a little bit in trouble because we need to use the anti-commutation relations that we're supposed to derive here. So I'll give them. Yeah, we derive them in E officially. I'll give them. So they are gamma K prime 0 and gamma K dagger gamma K prime is equal, as usual, to delta K prime for as long as K is not equal to minus K prime. Yeah, so these are the anti-commutation relations you need. These anti-commute two alienation operators as well as two creation operators. If you have one of each, then they're always 0, except this one. Okay, so now we have all the ingredients we need. The starting point Hamiltonian here, and the commutation relations that apply. So we can set to work. How are we doing for time? Okay, let me see. Let me see what I wish to do. I will also give this as homework because I would really like to get to the equations at the end, and we have 10 minutes left. So let me see if I can give you a little hint, and then you can work it out for yourself.
My favorite symbols on balances. Out from the balance.
So if you follow this procedure, you will find the expression for EG, and you can express EG in terms of E0. So you will find, if everything is going well, this sum, again over the eigenvalues EK and gamma operators. And then there is one term extra that you have to subtract again, and that is for positive energies, EK larger than 0, a sum over EK plus E0. And this term here appears again when you use the anti-commutation, because there's always this one special point that usually gives you an extra term, one of the terms in the sum, and that gives you this. And now this is same as 12 if EG is E0, and then you subtract this term here. I'm going to use the Heaviside function to express that the energies must be positive. Okay. Yeah, this theta is the Heaviside function. So only the positive energies contribute. And now you see what is nice about this. And now you see here, now we're getting close to the quasi-particle equations. You see here that this Hamiltonian has two terms. The ground state energy, EG, and then any additional energy that adds to it, because EK is always positive. So as soon as there is one term here that is non-zero, energy increases. So this is due to the excitations, the quasi-particles. It's a very nice form, this equation 12. You can read off, and there's the ground state energy plus the energy of the excitations. Okay, now we're getting very close. F. Finally, we're getting to the equations that we want to do. F, in F we have to write down and also solve the BdG equations for a homogeneous superconductor. So we made a little excursion to an inhomogeneous superconductor in part B. Now we're going back to the homogeneous superconductor. That will allow us to write down these equations. Step 1. We have to use everything we have derived before, because it all builds up. So we're going back to equation 8, to the Hamiltonian, long time ago on the board, equation 8, and use, this was the form where the matrix elements, the H elements have the indices N and M, out in the electron hole space. So now use the following notation. N will now be representing wave vector and spin, K and C. And then you ask yourself, this matrix, that is in your notes, hopefully, which terms are left? Which terms are non-zero? Again, remembering that it's now a homogeneous superinductor. Yes, it is. So then, if I immediately use this notation, equation 8 still have the n and the m. I'm going to substitute this for those. So I find A, K, sigma, and K prime different index, also sigma. This is a non-zero term in the Hamiltonian, and let me call that epsilon K. Shorthand notation. So you see these are the diagonal terms. H was on diagonal, and the off-diagonal terms, those were the delta terms in this Hamiltonian equation 8. They are only non-zero if K sigma couples to minus K let me see, did I get, yeah, K prime is correct here, minus K prime minus sigma. And also here, we will use shorthand notation, sigma delta. So you see that this one couples opposite spins to each other, and electrons and holes. Couples E and H with opposite spin. All other terms do not contribute. That's a good question. I don't think you need it. Let me see if I did everything correctly. No, you don't need it. It's the same for all the for anything. Yeah, all the case. Now we are there, more or less, almost. Yes.
Is it minus K prime there or minus K?
Minus K. Did I write K prime? No, it's correct.
No,
Not minus.
Down,
Yeah. Ah, yes. Thank you very much. Minus K.
And
Yeah.
also in the tab one, why does like the epsilon K doesn't
Yeah. You're right. There's no index here. Yeah, very, very smart. Yes, I'm getting a little bit blind. Oh no, this is this is good. Okay, so let's substitute this in the matrix, in the 2 by 2 matrix. And then with this, now that we have identified non-zero terms, you can write down the eigenvalue. And I'm going to make a choice here. I'm going to look at an electron with spin up and a hole with spin down. But you can also make the opposite choice. So choose electron up, hole down. Then I have epsilon K on the diagonals. Minus sign here. Epsilon K minus epsilon K. And here it's delta and delta star. And now I'm going to call this wave function because I'm still in this electron hole space. So I'm going to choose the notation, electronic part of the wave function, electron-like part, hole-like part, eigenvalue, let that be Ek, we have to determine it, and then there's again the wave function. So these are the solution for the eigenvalues. Can you see it immediately? And you can derive it from the 2 by 2 matrix. Yes. EK is two solutions, yes. Plus minus. Square root, yes. Epsilon k, just like that.
Plus absolute value of
Squared. I'm hearing from different directions good things. Delta squared. That should be it. So these are the two eigenvalue solutions, and the eigenvectors, finally, belonging to these two solutions. For the plus solution, we will find, aha, and now we can make a nice connection again to the book, because there, UK and BK, you remember? Yeah? So this what is called psi E here, the electronic part of the wave function, is nothing but UK, and the whole like part minus BK. That's for the plus solution. For the minus solution, it's the opposite, or less. Psi is then equal to BK, and the whole part is equal to UK. And the same you can do if you take an electron with spin down and a hole with spin up. Really small changes here in the signs, but a very similar solution. G is again for home. In G, you have to do the same exercise. Write down the BdG equations. Don't need to solve them, only to write them down, but now in coordinate representation. For the same effective Hamiltonian, in coordinate representation. Also, then you have kinetic part of the Hamiltonian, potential part of the Hamiltonian, and you find a similar 2x2 set coupled differential equations. Procedure is the same as in F. We have reached the end of exercise 11. No time left, I'm afraid, for 13, which is also very nice. It's about the PSS landscape. Have a go at it at home. Good practice. I will leave the last 2 minutes to Yuli. Maybe he wants to say something?
Oh, well,
Maybe not.
I've been talking today too much already.
Okay.
Good. Thank you for your attention. See you next time.
Good luck with the homework.
About a half actually has made homework already.
Really?
Yeah.
Oh, you have
It's
it.
very
Oh.
diligent generation, it seems.
Wow.
I will end this meeting.